Algorithmic music composition has a long history and is certainly not a new task. As early as ancient Greece, the philosopher, mathematician, and music theorist Pythagoras documented the relationship between music and mathematics that laid the foundation for a modern study of music theory and acoustics. Later, as musical complexity developed, as sacred and profane music rose, composers kept toying with the idea of algorithmic music. One of the more notable examples from the classical period era by everyone's favorite musical genius, Mozart, the Musikalisches Würfelspiel, where he composed a set of discrete musical excerpts that, when assembled together, would form a waltz, of which the structure was to be determined by rolling two six-sided dice. Ever since, the enthusiasm has not wavered. In 1966, Xenakis, an alumni from the Athens Polytechnic School who studied music composition with big names of his time such as Milhaud and Messiaen, founded the School of Mathematical and Automated Music in Paris. His music, described as stochastic music, uses probability theory to select musical parameters. For over 2,000 years, composers have used algorithms to assist in the creation of music, so it's really not surprising that deep learning has also been used in the context of music generation or composing. At the heart of modern-day deep learning is the multilayer perceptron, MLP. They are a deep artificial neural network whose learning strategy follows this process. First, we minimize the global error function for the input dataset. Then we use backpropagation to pass that error back through the network and update each neuron's weights. A subclass of MLPs called recurrent neural networks, RNNs, are essentially MLPs that have the ability to take time and sequence into account, considering information in its context. Essentially, they have a feedback loop allowing information to persist. As you can imagine, this is a critical feature to generating coherent music as they are sequences. A subclass of RNNs are long short-term memory networks, LSTMs. Those are essentially RNNs that are able to learn longer-term dependencies thanks to a more complex cell structure. And we could use those LSTMs to generate music, which is exactly what we have done. We trained an LSTM network on the entirety of Maxwell-tempered clavier 2 pieces, which we parsed like so. We first turned the MIDI files into a list of notes and chords. We then defined each note or chord to be one class, and finally we defined our training dataset to have as input a fixed length sequence of notes or chords, and as output the note following that sequence. So for example, if our sequence length is 100, then the 100 notes would be the input and the 101st note would be the output. Training was completed successfully in about 30 hours on a cloud machine with GPU compute. We can take a listen at the result. We can actually compare that to some fully random music, which we will generate right now. So the way this music is generated is by picking notes at random from all the notes seen while parsing the input training dataset, which is all the back pieces that we're training our model on. So as you can hear, this is much messier and, nowhere near what an actual human composer would come up with. How about now we generate some music using the model this time? We can listen to that music now. And hopefully you will agree with me that this sounds considerably better than the fully random music, and that the music generated by the model sounds at least somewhat realistic. However, if you listen closely, you will notice that the generated music lacks depth, color, emotion. This is mostly due to the fact that in the way we parsed our data and defined our classes, we did not allow any room for different rhythms, polyphony, intensity or volume indications, tempo, etc. We only took into account the pitch of a note. In an effort to resolve these shortcomings while looking at another more recent method to generate music in the field of deep learning, we implemented a generative adversarial network, or GAN. Fairly recent, they were introduced in 2014. They are essentially two networks working against each other, a generator, G, tasked with generating music from random noise data, and a discriminator, D, tasked with discerning the real music from the fake or generated one. This essentially means that the training process is a zero-sum game, meaning that one's gains are balanced by the other's loss, where we consider training to be complete once we reach the Nash equilibrium, defined as when each player is assumed to know the equilibrium strategies of the other players, and no player has anything to gain by changing only their own strategy. In our case, this means when G produces data that D cannot tell from real data. To simplify, the training process follows 3 main steps. G first generates a music sample from random noise data. D will then look at that generated sample as well as look at the input training dataset, which is the real music, Bax music, and try to determine which one is real and which one is fake or generated. This gives us the loss function from which we can derive the gradients and use that to update the weights in both our models. Note that G and D here are LSTM networks, which is the same type of network as in our previous experiment. We change, however, the way we parsed our data. Before, we were only taking into account the pitch of the note. This time, we're taking into account 4 features per note. The pitch of a note, the note length, so the time between the note on and note off event, the intensity of a note or volume, and the time spent since previous note. For example, if this value is 0, then this note is occurring at the same time as the previous note, essentially taking into account polyphony. As you can imagine, such a training process is quite volatile and arduous and takes quite a long time to converge. However, we can take a few steps to attempt to make it more efficient, faster, and more stable. Which is why we pre-train our models separately and directly on the training dataset for a few epochs. We also implement freezing to prevent GRD from getting too strong with regards to the other, meaning that if D's loss, for example, is less than 70% of G's loss, then we freeze D's update to allow G to catch up, and vice versa if G is too strong. We also implement feature matching to prevent the training process from turning into a never-ending cat and mouse game. We do this by changing G's objective from simply trying to beat D to minimizing statistical differences between G's generated music and actual music from our training dataset. Even with such optimizations, the training process of GANs is long and arduous. Reaching 72 epochs took around 2 days, while the previous experiment reached 200 epochs in 30 hours. This is all I was able to do due to time and resource limitations. Nonetheless, we can listen to the sample generated after the 72nd epoch. As we can hear, the music is much less realistic, much further away to what a human composer would produce. This is due to the network not having received appropriate training. However, we can still notice its potential, as this time it takes into account different volumes, notes of different lengths, the possibility for multiple notes to be played at the same time, all of which are key elements to creating realistic sounding music and not mechanical sounding music. This method is quite promising, and with appropriate training, the model could achieve better sounding music. The field of music generation using deep learning is a very promising one, with advances being made every day to create more realistic music, make the process more accessible to encourage musicians and programmers to give it a try. The barriers of entry to this field are lower than they have ever been, and interest higher than they have ever been. Just 2 days ago from filming this video, OpenAI, a non-profit AI company backed by Elon Musk and Reid Hoffman, released MuseNet, a deep neural network that can generate 4-minute musical compositions with 10 different instruments and can combine styles from country to Mozart to the Beatles. Today, these methods are good enough to create convincing music, but nowhere good enough to craft a Grammy Award-winning song on their own yet. But there is no telling what tomorrow's music generation techniques will be able to do.